Okay, I think it's about time to get started. I'm gonna go for chapter one. It's gonna be talk about the fundamentals of machine component design. That what I mentioned earlier on the day that what I mentioned about the course syllabus. I mentioned about it before on the mechanical engineering design. That what I mentioned that's gonna be utilization of the combinations of the things that what you guys studied about it before on the year number one and year two, things like that. And what the combine of the material engineering design course, and then engineering mechanics, and then solid mechanics. We're gonna combine it together, and then in order to obtain an appropriate machine's component size, things like that, and then we're gonna manipulate on the strength of the machine's components and the cores that what we manipulate on it. And then therefore in order to obtain all those kind of matter that what I mentioned on it, we gonna review all the things that what you guys just made on it before. That what is gonna be the stressed. Anyway, the stress that what we ever studied about it before, it's gonna be the things that what defined as the force per unit area or the intensity of the force distributed over the given sections anyway. So therefore the stress can be defined as the normal stress. If this is gonna be defined as the stress distributed over a given section under the axial loading. Okay, it's denoted by the Greek letter of sigma, and then it's be sub classified as the tensile or the positive manner as a positive, and compressive is going to be in the negative side, respectively. And we'll show you guys on the figure A and B, respectively. And what you up there, see, is going to be on the tensile, is going to be a positive. Therefore, on the figure on the left is going to be a positive. The inside is going to be the cross-section area. We're going to small force distribute all over the given sections here. And then on the right-hand side, we're going to have a compressive stress. We're going to have compression force right there. And then it compress all the way, distributing over the given section there. That what you might add up the sigma t as a tensile and then sigma c as a compressive respectively. And then another one is gonna be confuse me a lot when I was a student like you. Okay, that would be a shear stress. Of course, it's gonna be denoted by the Greek letter sub tau. Anyway, it's gonna be is the force distributing over a given section under the shearing force, of course. You may figure out the figure there. We have a force and then we have a pin inside between the two plates there. You may figure there the force of F there parallel. Okay, I emphasize the force of F there parallel to the given of the cross section to the pin there. So the tau there is going to be equal to the F over A there. So there is going to have a dimension of the stress. F is going to be in the Newton sort of way. And then the area is going to be in millimeters square so all the way. So therefore the dimension of the stress is going to be in meganewton, megapascal, or 1 of Newton per square of millimeters, respectively. Another one, it's going to be, another one is going to be in terms of the bearing stress. Okay, it's going to be the things of the stress we define as the stress induced at the surface of contact or the bearing surface by the assembly of the machine parts. So it's mean the bearing stress only induced when we have the machine parts assembly to each other. As this figure just show you there, we have a box there, we have a machine part just insert inside or the pin insert inside. It mean action and reaction. So it's mean the pin just insert a action force to the box and the box at the same time have a reaction force exerts on the pin. So therefore, this one is going to have a surface of contact. It's going to be projected area there. So therefore, this one is going to have a bearing stress of F over A. A is going to be equal to the projected area. Is going to be the L times D respectively. L times D is going to be the projected area respectively. Okay, another one that what we gonna be very progressive applied on the manufacturing process a lot. Anyway, that what it's gonna call residue stress. Anyway, it's gonna be the stress typically induced by the treatment during the manufacturing process, such as forging, cutting, bending, pressing, and heating, and etc. This kind of thing is gonna for the modern technology. We apply a lot for the common manufacturing process. A lot of car factory have been use a lot of this technique for those kind of residue stress for applied for the workpiece on it anyway. So we're gonna show you some of the things that what we just do on it for today's technologies anyway. Okay? All right. Just rather than the stress, of course, that what I mentioned a while ago. Anyway, we talk about the stress. When we have a stress, we're gonna have strain respectively. The strain can define as the deformation. Okay, I would like you guys to underline from the deformations in a way of the member, strength length due to the external loading. Of course, everything just happened due to the external loading of F. When we have F, we have a stress, and then at the same time we have a strain respectively. Therefore, in this figure, see we have applied a load of F there. So therefore, we have elongation of delta. So delta there over L, we call it strain. So therefore, the strain is gonna be delta over L. Is gonna be the dimensions of millimeter over millimeters. So therefore, the strain we have a dimension less than. So therefore, the strain, for instance, for example, we have a member have an original length of 100 millimeter, experiencing elongation of 1 millimeter. So therefore, we have a strength of 1 over 100 is going to be 0.001 then. It mean nothing for us anyway. So therefore, if we present it in 1%, it mean a lot. We can sense it up by percentage anyway. Okay. So if we just based on the Hooke's law anyway, we're gonna apply more, explain more and more in terms of the Hooke's law anyway. For under elastic limit, we're gonna explain more and more in terms of Hooke's law and elastic limit after this anyway. Okay. So therefore, the relationship is gonna be under the Hooke's law. We have a sigma equal to E times epsilon. We're gonna talk about it in more details after this. So therefore, I make substitution of sigma equal to F over A, and delta is going to be equal to epsilon time L. So therefore, I got another relationship of delta equal to F time L over A time E respectively. So this is the relationship that we've got rather than the sigma equal to E time epsilon there, okay? And then another important thing that what I typically would like to pay a lot of concentration on the stress and strain relationship. Anyway, see, this one very important. So we just all the things mentioned about this kind of thing mostly anyway. So this kind of thing we typically do on the lab experimentations anyway. Okay. So therefore, typically, if I would like to know about the stress and strain relationship for typical types of the steel that what we've got there, for example, I would like to ask you guys what is the typical type of stress and strain relationship of the steel that what we use in Thailand, things like that. So you may go to Samyak and say things like that, and go grab it, and then you just make a lab test, things like that. Okay, you just go grab a piece of steel there, okay, as Samyak said, and then you just pick it up, and then you go to the workshop there at the IPT, and then you just do some of the latent machine, do all the process to be look like this. Okay, and the test specimen of the tensile test is gonna look like that, and then you put on the ATM UTM machine. Okay, testing machine look like that, and to the lab test, things like that, okay, and then you put it up, okay, for, okay, the left hand side, okay, for the ductile material, okay, this is the steel type anyway, ductile material, okay, this is the ductile material is steel all the way, but on the right hand side is kind of brittle material. The material on the right hand side is gonna be some kind like a ductile out of the, I'm sorry, this is the brittle material, like a cookies, okay. For instance, like see this type of brittle material is going to be the things that what uh, very strong, but is stretched up to the point. It's going to break into pieces, things like that. Okay. So therefore, the thing is going to be on the left hand side is going to be some kind like a steel, and this is going to be some kind like a cast iron on the right hand side. Okay. So let's go for the experimentation first on the left hand side. Okay. On the left hand side, okay, we can go for it for the experiment. Okay, we're gonna put it on, okay, on the UTM, okay, testing machine. Okay, we put it, okay, on the way. Okay, we just do experiment, okay, first. Okay, so therefore we put it from 0 point here. Okay, we have a sigma. Okay, sigma is equal to F over A there, and epsilon is equal to delta over L. So the students can make a lab test there. So we plot it out. Everything's gonna go from 0 to point of A there. Okay, so therefore everything's gonna go straight line, things like that. We have a plot of the curve there. So therefore, we just take an experiment and then we take and force out things like that. Everything gonna get back to the same shape there. So everything's experienced on O to A there. We call it proportional limits there. So therefore, 0 to A here, okay, we gonna call it 0 to A. We call it proportional limits. That's what I mentioned there. Okay, so therefore everything is being a stress and strain have a straight line there, or we call it as a proportional limit. It mean, okay, sigma equal to E times epsilon. The slope of the graph here is going to be equal to E, or the Young modulus, that what we mentioned about it before. Okay, and then from A to B, it's not a straight line anymore. Okay, it's gonna be very close, but I enlarges. Okay, but typically A to B is very small there. From A to B there is going to be very small, but typically this one I enlarge it. Okay, but A to B there, so this one is no longer is gonna be not a linear, not a straight line anymore. So therefore, A to B is still under elastic limit. It means we just expelled out the force. Everything gonna get back to the same shape that what we have done it before. So it's under elastic limit. So it's nothing damaged yet. Okay, but this one A to B is not a straight line. So therefore, the equation is not sigma equal to E times epsilon anymore. The equation might be sigma equal to E times epsilon to the power of n, because this one is going to be a curve anyway. So therefore, this one, okay, is still under the elastic limit. Okay, so 0 to B we call elastic limit. See, elastic limit is there. So the last portion where the material behave permanent elongation. So it's been this one till we expel out the force, everything can get back to the same shape then. Okay, we still make an experiment more, so therefore reach up to the C point there. C point here we call U. Okay, U point is mean everything's gonna break out inside. Means the bonding and everything is gone. Okay, it's been damaged already. So therefore something happened inside there. So therefore something damaged inside. So therefore that C point there. It's starting some kind like permanent elongation. Okay. So something happened, something not good there, so something damaged inside. So therefore it reached something damaged inside already. So therefore, okay, at the point C there, we call that yield point. Okay, the sigma y, which can be found from typical table of the mechanical properties of material, the typical type used as design strengths of the material. Okay, and that what you guys study about before in solid mechanics. This is gonna be the U point. That's the point there. Gonna be the reference that what we uses a lot for the design is mean the stress never ever reach up to this point. When we just design it, we use as a principle of the design. We never allow the stress induced inside the workpiece to exceed up to this point. Okay, so this is the thing that what we keep in mind about it. So we do experiment more. So the stress is increase more to this point. So it's reach up to point C. So everything damaged. So it means everything's going to be damaged already. So therefore everything's going to be damaged inside. So at the point B and D there, so it's been damaged already. So it means C at B and D there, the B and D is going to be damaged. The size of the things is going to be reduced in dimension and elongate. So therefore, the dimension of the cross section is going to reduce. And then it's going to be, see, the point B and D is going to be the sigma equal to each other, but the strain have been a lot at point D there. So therefore, this one is going to be more at point D, and then it's enlarged here, and then we experiment more and more. But this one, see, you may figure out it's damaged inside all the way. It's going to reach up to the point E there. It yet be damaged outside, but inside it's been damaged already. But this one, see, you may figure out a lot of elongation. So therefore, the cross section gonna be thinner and thinner already. So this one, see, it's to reduce a lot of the cross-sectional area. So therefore, we have a sigma u there, and then so we still make experiment more and more. We just reach up to the point of F there. So therefore, everything's gonna be break out failure, the cause of failure. It means everything tears apart. At this point, everything can be totally damaged. Okay, so this one up to this point, okay, we call it failure. Okay, so therefore the sigma u is gonna be the maximum point there. So therefore we call it ultimate strength tensile strength. Okay, that's what we call the sigma u ultimate tensile strength. We can be found from the table of mechanical properties of the material there. Okay, so this one is going to be the things that what we just talked about it. Okay, this is the ductile material. Okay, and then another one. This is typically this is a steel. Okay, this one is going to be cast iron. This one we never ever have a sigma y. This type of material we just make experiment. Look like the workpiece look like that. See, it's gonna reach up to the highest point there, and then we reach up there, and then it's gonna reach up to the point E there, and then it's gonna reach up to the point F, and gonna break up into pieces. Okay, but sometimes, see, we just wonder, okay, we like to find some the sigma y, okay, we just do another way around. We just to try the sigma 0.2 or 0.2% offset method anyway. We just make it like this anyway. We find a 0.2% offset right there, and then we make it parallel to the graph there, and then intercept up here, and we make a projection back here. Okay, you guys just do it like that. Okay, and then we make a projection, it will be back here, sigma 0.2, or estimated to be around sigma y here. Sometimes we just around to be a sigma y of 0.2 anyway as the estimation of the sigma y sometimes then. Okay, all right, this one is gonna be the things that what we gonna estimation for this sigma y rather than a sigma u for the brittle materials anyway. Okay, so therefore this is the things that what I explain on it for the sigma y, then the sigma u for the brittle material and the ductile material respectively. For the tables of the mechanical engineering contents of the tables of the material, we typically don't have a table of tiles. Anyway, we can make an estimation of the tiles of Y typically by tiles of Y and tiles of U to be about zero point 0.6 sigma Y and tiles of U about zero point 0.6 sigma U respectively. And the Young modulus and the shear modulus of the section 4 we're gonna have for the steel equal to the sigma over the epsilon. For the steel, typically we're gonna have about 207 gigapascal. For the aluminum, we're gonna have 71 gigapascal respectively. And for the G, okay, term for the modulus of rigidity, for the steel we have 73 0.3, and then G for the aluminum we have 26.2 respectively. Okay, this is the thing that for the reference of the steel and aluminum respectively. Okay, for the safety factor, of course. Okay, this is the things that what gives you some hinge or something that for reference anyway for you guys when you just use for the design anyway. See that what we just see the graph there, we gonna all the way use a sigma y, okay, as a reference. So therefore typically we're gonna use a n sub y as our reference for the design anyway, and n sub u is gonna be a second reference anyway. See, therefore, see, we typically use the table 1.1 as our reference. Okay, I always use a table 1.1 as one of my reference all the way. See, for instance, like the line number 1, if we know everything sub, that what is the typical things that what we never ever find it. Okay, this one is very difficult. See, everything is no echo lately. That was impossible anyway. That we got it 1.25 up to 1.5, things like that. Typically, we just got to know about the number 6 is going to be uncertain all the way. See, estimate to be about 3 to 4, things like that all the way. See, and then we still doubt about it. We're gonna, I mean, add up some more factors on it. Okay, and then number 3 there for the note C, if the impact factor, use the number of the impact factor and add up more. And then number 4 for the brittle material, see, for number 1 to 6, if you use number of the sigma u there, you just double the number of figure there. See, so this one is going to be reference that what I always use it. Okay, it's very dangerous there. If you just doubt about it, you just make more in number of safety factors anyway. Okay, this is the reference anyway. Okay, I'm gonna stop it for a while, take a break, and then we're gonna go for the numbering system. Gonna go for it. Okay, after this anyway. Okay.